Good morning. I hope you all had a great weekend. I'm honored that you're here. Today at 1:10 p.m., Midterm Exam I is going to happen. Show me what you've learned, all right? Shouldn't be too crazy and stuff, but I just want to see the things you've learned. It's over problem sets 1, 2, and 3. So basically chapters 1 and 2, a little bit of 3, sig figs, temperature, density, metric prefixes, Coulomb's law, thanks for that. Avogadro's number, definitely grams to moles to atoms, grams to moles to molecules, molar mass, also then naming, and empirical formula, molecular formula kind of stuff. When you come today to class, you'll turn in Exam Prep 1, which is a worksheet. It's right after problem set 3 in the companion, or you can get it online. Empirical formula lab from last week you'll turn in and bring a printed copy of the percent potassium chlorate lab, in-class lab. This is kind of a fun lab. Your safety goggles will be needed. We're going to burn some stuff pretty intently, see how much KClO3 is in it, just like that. 20 multiple choice questions, 4 short answer questions. Your exam will have 5 points of extra credit in the short answer section, so just fill it all out. And then when I return the midterm to you, which will be next week, you'll have a summary sheet kind of saying like how you're doing in the class as of this time. And I do encourage you to check it out just to make sure that your assignments are turned in, the grades that I have reported are the ones that you actually got, stuff like that. Questions? All right, we'll do a few more exam review questions, and then after that we'll start looking at how to balance chemical equations and stuff like that. Okay, so here's a question. We have a nitrogen-oxygen compound, and we're just putting X and Y up there because we don't know what their formula is. And the percentage of nitrogen, 46.67%. Oxygen would be then 100 minus this number. And the question is, what's the empirical formula of this oxide? And what I would recommend doing, turning percentages to grams, grams to moles, compare the moles. But you had a really cool idea on Friday that would work here because nitrogen and oxygen's molar masses are about the same. So by hook or by crook, see if you can figure out which of those would be the best answer, and we'll talk about it here in a little bit. When you have a formula, like any of the answers are right there, those are mole-based formulas. So N2O means 2 moles of nitrogen for every 1 mole of oxygen. And N2O5 would be 2 moles of nitrogen for every 5 moles of oxygen, stuff like that. So if you have a percentages, these are mass-based, which means grams, all right? And you've got to convert the grams into moles. So over here on the blackboard, I just take 40, I just assume 100 grams. So that would be 46.67 grams of nitrogen, and 100 minus 46.67 is 53.33%. That would be 53.33 grams of oxygen. Then these numbers come from the periodic table for nitrogen and oxygen. Usually going to 100th is great. So for nitrogen there, it says 14.0067. I just called it 14.01. Oxygen would be 16.00 grams. So you don't have to use like all the digits. It makes your life a little bit easier. Whatever you get, that's literally the X and the Y in this formula. And you can then compare them, divide the bigger ones by the smaller ones, stuff like that. Either way, it comes out to be almost exactly a 1-to-1 ratio of nitrogen to oxygen. If you want to be absolutely certain, divide both of them by the smaller, which is 3.331, and you should get 1 nitrogen to 1 oxygen, or NO. So this thing looks like it's nitrogen monoxide, something like that. So percentages to grams, grams to moles using periodic table. Compare the moles. Good to go. Question? Okay, here's a problem that's kind of like what we did in lab last week. In this compound, we've got a zinc oxygen compound. We don't know the formula of the zinc oxygen compound, but we do know that 6.54 grams of zinc with some oxygen gives 8.14 gram of a compound, a zinc oxide compound. So we're assuming here that all the zinc is gone and there's no zinc left. This is a similar kind of problem. You want to find the grams of zinc, which is this number right here, converted into moles of zinc, so you look up the molar mass of zinc. And then 8.14 minus 6.54 will be the grams of oxygen. And you'll divide it by the molar mass of oxygen to get moles and compare. See if you can do that to find the right answer. Check it out. So the last example, the previous one, was if you send it away for analysis and they send you back the percentages of the elements, you can find the empirical formula this way. This is more of an experimental procedure where you're actually reacting the chemicals. And this is kind of what we did with the copper chloride. We had so many grams total of the copper chloride. You isolated how much copper, the red copper was left. You could find the chloride from the difference, blah, blah, blah. But again, like last time, these are all mole ratios. It's not grams ratios, these are mole ratios. So the best way to do it is to find the moles. So up here, 6.54 grams of zinc apparently reacted. Divide it by the molar mass of zinc from the periodic table to get the moles. And then 8.14 minus 6.54, that number, 1.60 looks like. That's the grams of oxygen divided by molar mass to get the moles of oxygen. That's the X and the Y. Make it equal. But anyway, the moles come out again to be basically exactly the same to 3 sig figs, 0.100 moles of oxygen and zinc. So that makes that pretty chill. It's zinc oxide, ZnO. And hopefully this isn't too shocking because zinc is one of the stairs. And aluminum, gallium, indium, those are all +3 metals. Zinc and cadmium are +2, silver is +1. So if zinc is +2 and oxygen in group 6, 6 minus 8 is -2, they should come together in a 1-to-1 ratio. So ZnO makes sense on that level too. But again, the process is just grams to moles, compare them, find the empirical formula. Questions? Once you have the empirical formula, you're not quite done as a chemist because you need to figure out what the molecular formula is. So in this problem, we know that the empirical formula, the smallest whole number ratio of atoms, is CH2O. And the whole compound, through a separate experiment, has a molar mass of about 90 grams per mole. So the question is, what is the molecular formula of the compound? So it'll be CH2O taken once, twice, 3 times, 4 times, whatever. See if you can figure out what the molecular formula is of this compound. molecular formulas are always an integral number of empirical formulas. And so what I mean by that, if you have CH2O and you take it one time, that would be CH2O, and that is a valid molecular formula. But it could also be CH2O taken twice. So that would be C2H4O2. Or it could be taken 3 times, C3H6O3, etc., etc. So A, B, C, and D, if you look at the answers, those are all integrals of CH2O, and those are all totally valid. But answer E wouldn't make any sense here. The ratio of the hydrogen to the carbon and oxygen is incorrect. It's 1 to 1 to 1, and you can see it's 1 to 2 to 1. So to find out how many X's, how many empirical formulas you have in your molecular formula, it's always going to be a whole number ratio. And the molar mass of the whole thing, which is given to you, by the way, is going to be the numerator. And then in the denominator, you want to figure out the molar mass of the empirical formula. And you can use real cheesy sig figs here. They don't have to be real exact because the X is always going to be a whole number. So carbon's about 12, hydrogen's about 1, and there's 2 of them, and oxygen's about 16. So 12 plus 2 plus 16 comes out to be about 30. So you can tell here I'm really just using cheesy sig figs. 90 divided by 30 is all we need here. So 90 divided by 30 is a ratio of 3. These X's always whole numbers, no fractions or anything like that. So if you figure out that it's 90 divided by 30, a ratio of 3, then that means that your molecular formula will be that empirical formula taken 3 times. So 3 times CH2O makes answer C, C3H6O3, the right one. Questions? So a lot of times as a chemist, someone gives you a compound and they say, what is it? You have 2 things to do. You send it away for analysis. The first analysis, you get the percentages, which lead to the empirical formula. The second thing you do, though, is you send it for a molar mass value, like this one right here, and you can compare the molar mass of the whole thing to the empirical formula to find the molecular formula. Questions? Yeah. All right. So this question kind of pulls both of those ideas together. We have a compound. It has phosphorus and fluorine. All right? It's 75.41% fluorine. So that means 100 minus that number would be the percent of phosphorus. And from just those 2 percentages, you can find the empirical formula of the compound. But then, once you have the empirical formula, I'd like you to find the molecular formula using the molar mass. So once you have the empirical formula, that to the factor of X is going to give you the molecular formulas. So down here, 251.94 would be in the top, and the molar mass of your empirical formula would be in the bottom. So see if you can use all that information to find out what the molecular formula of this phosphorus fluorine compound will be. So the molecular formula is kind of like the holy grail of this first section of Chem 221 material we're looking at. And if you can find it, it's a great step toward being a chemist, identifying things, stuff like that. Percentages to grams, like we've done already. So 75.41% became 75.41 grams of fluorine. And then 100 minus this number, 24.59%, I made 24.59 grams of phosphorus. And then grams to moles, these numbers here come from the periodic table. That gives you the moles of X and Y, moles of fluorine and phosphorus. So you can use that to find the empirical formula, divide the bigger one by the smaller one to get whole numbers. Then you find the molar mass of the empirical formula and put it right there. The molar mass of the whole thing, which is something that's given to you, goes on top. This will be a whole number ratio. So the molecular formula will just be that empirical formula taken so many whole number times. That's kind of the idea. If you put this all in, here's the math. So 75.41 grams of fluorine to moles gave you this number right here. 100% minus this is where 24.59% came from. Turn that to grams to moles, 0.7940. So this is a formula, but it's ugly. So divide both of them by the smaller number. So 0.794 is smaller than the phosphorus mole, so we'll divide them both. So that gives 1 mole of phosphorus. That divided by that is almost exactly 5. So PF5 is the empirical formula. If you add up a phosphorus and 5 fluorines, it comes out to be this number. That goes in the bottom, the molar mass of the whole thing on top. You get a whole number ratio always, in this case 2. So twice PF5 gives you P2F10.
Yeah. When you multiply both by 2, is that only minus 7.5?
When we multiplied by 2, we already had the PF5 part. And yeah, you do both of them by 2. So like P times 2 is P2 and F5.
Sorry, I meant that if the empirical formula, if it wasn't 4.99, if it was like 4.5.
Right on. If it was 4.5, then absolutely this would be a time to double it, so multiply by 2. In problem set 3, there was like a, I think it was N101.5, and you can't have half atoms, you're right. So then you would multiply by 2, that's right. I won't give you anything but halves, all right? This one will always be a whole number though and stuff, so excellent comment. Yeah. Sure.
I was actually put the PDF might be great to me. Which one goes first again?
Cool. So this is something we're getting used to, and if you wrote this as F10 P2, it's totally fine. All right. In organic chemistry, carbon's always first, hydrogen's always second, oxygen third, nitrogen, phosphorus, and sulfur would fight for the next place. But honestly, at this point, you can call it F10 P2, and that's okay. All right. Don't worry about it. Other questions? Yeah. All right. Iodous acid is the name of an acid which isn't real common. And I'm just going to kind of show this to you just to talk about it a little bit. If you want to participate, that's awesome. But there's a whole series of these hydrogen iodine acids. Now, without any oxygen, it's a hydro. So anytime you see hydro, it means there's no oxygen to it. So hydroiodic acid would be HI, no oxygen. And then iodate, the ATE polyatomics are supposedly the most common. And the ATE polyatomic, iodate, when it's turned into an acid, that gets the ic acid. So supposedly HiO3 is then, except for HI, the most common acid. That's why it gets iodic. And then from the common ion, you can see that -1 oxygen, that's when you get the OUS ending, so iodous acid. You can go down sometimes even one less oxygen, like in this case to HIO, that gets hypoous acid, hypoiodous acid. And then sometimes you can even add an oxygen from the most common one. So there's IO4, That's a per-iodic acid. So I'm just kind of pointing it out there and stuff to show. This works really well for iodine, chlorine, and bromine. So you could have a chlorous acid or a bromous acid. It does also help if you have nitric acid and nitrous acid, because the us acid has one less oxygen than the most common one, the nitric acid, stuff like that. So I'm just kind of putting it out there as a reminder about these crazy names. Questions on that? Cool. Another thing I want to talk about in naming real fast is if you have a hydrated compound. Now, hydrated compounds aren't super common in chemistry, but they do exist. This is when the water molecules bond to usually a transition metal, sometimes a regular metal. And when they do, they form really neat colored compounds. So in our empirical formula lab, that cool blue compound you started with, that was the hydrated version of the compound. There were waters on the solid. If you need to find the molar mass for it, it's important that you add the waters in, and that's why I'm putting it up here. Now, nickel 2 nitrate, nitrates -1, NO3 -1. Nickel 2 means a positive 2 nickel, so you'll need 2 nitrates for every 1 nickel. But in this case, it's a hexahydrate. So that means hexa is 6. That means 6 waters. So when you add the 6 waters to the molar mass, they're usually a lot bigger. So this one would be about 291 grams per mole. So if you see a hydrated compound, just make sure you add the waters in.
On the thing, on the last thing I had issues, like you said, find the moles in the, using the moles to find the empirical thing, like if you pour something to water, so how much
that might be a cool question to ask me after class. Yeah. So, in this case, though, I just want you to know that if there's a molar mass, just add the number of waters in and stuff. It'll always be a whole number, Michelle. I can say that too. And so if you see like 2.5 waters, you have the right to either round it to 3, or take it down to 2, or double it, whatever you think is right. So, but whatever compound you have, add the waters to the molar mass. Cool. All right, so that's it. Let's get out of this review stuff, I'll tell you. Today at 1:10, we'll do that. It'll take care of business, 20 multiple choice, couple short answer questions, stuff like that. The next section is going to talk about the power of the chemical reaction. And in chemistry so far, we've talked about the elements, and elements are the building blocks of everything. We took the elements and made compounds, so things like water, nickel 2 nitrate, et cetera, et cetera. Now we're going to see how the compounds themselves can make what's called a chemical reaction. And an analogy to what's going on here is the English language. And in the English language, there are 26 letters, and those 26 letters make thousands upon thousands of words, and words go into sentences. And the chemical reaction is kind of like a sentence, where you can sometimes use just the letters themselves, or you can use words, but there's a meaning for it, all right? And the chemical reaction is kind of like a sentence. So we take our letters and make the words, and words go to sentences. Well, chemists take the elements and compounds to make the chemical reaction. And there's a lot of power you can get out of this. It's pretty cool. Chemists get paid for making things, as you can probably imagine. Making things or identifying things or separating things, something like that. And this is it's the power of the chemist, if you will, unleashed. So this is just making zinc iodide, lots of energy released, pretty exciting kind of stuff. At the end of this section, you too will know how to use a chemical reaction to do some cool things. If this seems daunting, please don't let it be so, because really a chemical reaction is basically just chemists in the kitchen, chemistry stuff. All right. Now, in the actual kitchen, you would make cakes and sandwiches, and you can eat things, which is cool. You wouldn't probably want to eat things in the chemistry laboratory, but it's a very similar process. If you're making a cake, you need flour and eggs and oil and chocolate, whatever, to make the cake. There's a reactant amount. All right, you don't want to add too much flour or too little flour. You don't want to add too many eggs or too little eggs, or maybe no eggs at all, whatever your recipe is. But there's a way to make the cake that comes out, which is really cool. And chemists do the same kind of thing. We put in so many chemicals to make our end result, all right, whatever. We put in too much, we don't have as good a result as if we do it, or we can put in too little. Now, in chemistry, sometimes in cooking, but definitely in chemistry, if you're not careful, then you've got a lot of energy released, and you can have flames and fires and stuff like that. So, in the kitchen, maybe not, you need some kind of glasses, but in the chemistry laboratory, definitely important, all right, really, really important to have this out. So all the things we're going to talk about, you can literally think about as chemists in the kitchen, but it's a laboratory, so it sounds more official, but I promise it's the same thing, and I'll talk about that here.
He's a cook who works for the prisoners.
They say at the universities, you show me a chemist and I'll show you a great chef. What's the difference whether you have hydrochloric acid or a pot roast cooking on a Bunsen burner?
Okay, well, this is from Hogan's Heroes. Yeah, hydrochloric acid versus a pot roast. Anyway, there's a little bit of a difference. But anyway, sometimes people think that chemists are great chefs. Trust me, it does not apply in my case. But anyway, I do my attempt, and anyway, let's move on. Now, making a cake is fun. Sounds kind of exciting. I didn't have breakfast, so that's probably helping me. But this is a chemical recipe once you get used to it. And unlike a cake, which would be awesome, this is making aluminum oxide. And this is a reaction which can be really useful. So if we wanted to make aluminum oxide, we would add in aluminum and oxygen to make aluminum oxide. But we need to break down what exactly a chemical reaction is all about. So we're going to talk about reactants and products. Reactants are the pieces you put into the recipe. So the reactants in this case would be aluminum and oxygen. The products are what come out of your reaction. So the product here is aluminum oxide. So just like you can have flour and oil and eggs, those would be your reactants in making the product chocolate cake. All right, this is not as exciting, but it's the same idea. We would put aluminum and oxygen together to make aluminum oxide. Now, these numbers in front here are super important. All right, and the analogy is like you could have 2 cups of flour and 3 teaspoons of oil, something like that. Well, these numbers are really important for chemists too. We give them a fancy name. It's called stoichiometric coefficients, and you'll never have to spell it, but that's how you say it, stoichiometric coefficients. And they tell you the relative amounts of the reactants that go in to make the relative amounts of the products that come out. And they're very, very important. Another thing about this is you can see there's an S and a G. S and G, as well as A, Q, and L, will tell the chemist what the physical state of the compound is. So this is aluminum as a solid. It's not liquid aluminum. It's not gaseous aluminum. AQ means in water. It's not aqueous. This means that we're using gaseous O2, so it's not liquid oxygen. You can't have solid oxygen. It's tough to make, but you can. And the aluminum oxide that comes off says that it's going to be a solid. So sometimes you'll hear scientists say, like 4 parts aluminum and 3 parts oxygen make 2 parts aluminum oxide. Those parts are the stoichiometric coefficients. And we'll talk about more about what they mean here coming up. Now, not all reactions have states of matter. It is nice to have them if possible. If you don't, you can sometimes infer what they are, but if you have them, they're nice. And again, reactants on the left, products on the right. Yeah.
What was the L?
Oh, it's okay. Liquid. Yeah, liquid, that's right. L is liquid, and AQ, which really stands for aqueous, means dissolved in water. Other questions? That's a great question. Yeah.
Aqueous and liquid are different because liquid means it's just melted by itself.
That's right. Gasoline is a liquid. That would be when you use L. But if you have like iced tea, that would be iced tea in water. So that's when you would use aqueous. That's right. Good call. Excellent comment. Coffee. Thank you. Anyway, questions? All right. Here's another example. This is phosphorus reacting with chlorine to make phosphorus trichloride. Now let's look at the states of matter. Phosphorus is kind of a funky solid. That's it right there. It's kept in water to keep it safe from oxygen primarily. Chlorine is a gas. And when you add those two together, a lot of energy comes off, but you end up with liquid phosphorus trichloride. So there's no water here. So like both of you just said, which was really cool, yeah, you wouldn't call any of these aqueous. It's a pure solid reacting with a pure gas to make a pure liquid. And again, the parts here are important. This phosphorus is what they call a tetramer. You don't need to worry about that, but it actually comes as 4 phosphorus atoms at one time. One thing I do want you to remember, though, is that there's those 7 diatomics. Have no fear of ice clear brew. So chlorine is one of them. That's why we're putting a Cl2 right there. And then when all is said and done, you're going to make 4 phosphorus trichlorides. So these stoichiometric coefficients are great. Chemists can ramp up the amount if they want, or do it really small amounts based on these relative parts. So if you wanted to make, say, 10 cakes, you'd have like 10 cups of flour or something like that. You'd have bigger amounts. You would just multiply those relative amounts up to make 10 cakes, all right? Chemists can do this too. We could make these like 40 moles from 10 moles or whatever kind of ratios. They're really, really cool how they work out. Here's another example with a diatomic chlorine. Chlorine here is reacting with iron to make iron 3 chloride. Now again, chlorine, one of the diatomics, have no fear of ice clear brew, so Cl2. But iron is not one of those. And so you would write just 2 irons for this reaction. It doesn't have a 2 by because it's not one of the diatomics. And then iron 3 chloride over here is a solid. So a solid iron, gaseous chlorine, makes the iron 3 chloride as a solid. You can see that a chemical reaction happened in lots of different ways, and some of this we looked at in the 8 bottles lab at the beginning. Like if you see a solid form, that means that something happened. If you happen to see gas come off, if you see a color change, these kind of things, these are ways to see that there's color changes happening. Sometimes the temperature itself will be a factor. Like you'll feel the reaction get hot or the reaction will get cold. Those are the ways that chemists can see just with their own eyes and stuff that something has happened. Now, if you have a reaction like the aluminum oxide reaction, there's a couple different meanings here. An equation can mean that you have, on the atomic level, 4 atoms of aluminum reacting with 3 molecules of O2, and that makes 2 moles, or thanks for playing, molecules of aluminum oxide. So at the atomic level, that's what's happening. 4 individual ALs and 3 O2s come together, and they make 2 Al2O3s. But what we're going to use more often than not, and I babbled about there accidentally because I use it myself so much, is the mole level. All right. You can also say that 4 moles of aluminum will react with 3 moles of O2 to make 2 moles of Al2O3. This is kind of interesting philosophically to think about scientifically, definitely. But on a practical level, if you want to start making aluminum oxide, you've got to think about the moles. And again, from the moles, you can measure out the grams, that kind of stuff, to see what's happening. Any questions on that?
Mercury 2 oxide breaks down or decomposes readily when heated. If we were to weigh the compound before heating and compare its mass to that of the mercury remaining after the reaction, it would seem that decomposition causes a change in the system's mass. The product mercury would weigh less than the reactant. In reality, the decomposition liberates the reactant's oxygen atoms as gaseous dioxygen O2. All matter present before the reaction still exists after it. The reaction obeys the law of conservation of matter.
In the old days, I'm talking 1700s-ish, all right, scientists were really interested in what was happening on the chemical level, like why was this stuff reacting? So in this example, they took a mercury 2 oxide, HgO, and they heated it up. And if they measured the mass before and after, there was some mass loss, all right, and they didn't know what was happening. Now they knew that something was happening because HgO is kind of a clear solid, or like a white solid if I remember right. And at the end they have this kind of gray liquid kind of left over. So they knew that something was happening, they just didn't know what was happening. Well, now we know and stuff that, yeah, the oxygen gas was liberated. It's evolved out. O2 is a diatomic, have no fear of, ice clear brew. So O2 is there, and mercury liquid is left behind. But of course, at the time, they didn't realize it. So one thing that's really important in these things is chemists are really concerned about the mass that goes in and the mass that comes out. So scientists measured the HgO that was there before, and they measured what was left, which was Hg, we know now, and they saw that mass was lost. And that will trip chemists out, all right? Didn't bother the alchemists so much, but the chemists will be really worried about that. They want to account for the mass of what goes in. So one thing we're going to use a lot in this section is called the law of conservation of matter. And this is where accounting, if you will, comes into chemistry. And what that means is all the grams that go into a reaction must be accounted for on the way out. You don't want to lose or gain, for that matter, any mass along the way. Law of conservation of matter is a big part of chemistry. Now, a lot of people call it, and I will do this too sometimes, law of mass action. I think it rolls off the tongue better than law of conservation of matter. Same thing, all right? And again, all it means, all the mass that goes in has to be accounted for on the way back out. So in this case, the HgO had more mass than the Hg at the end. If you know about these things, then you can see that, oh yeah, oxygen is liberated and stuff. So law of mass action is a pretty important part of chemistry. Law of mass action was started by this guy. His name was Lavoisier. He was a French chemist, late 1700s. He was beheaded on the guillotine. He was politically on the wrong side of things, and anyway, ended up losing his head over it, which is too bad. His contributions to chemistry are pretty profound. This law equation, mass balance, law of conservation of matter is huge. He was also the one that proposed that you could have an equation that had to be balanced. And the equation that goes in, showing the mass that goes in, will equal the mass that comes out, stuff like that. So Lavoisier was pretty cool.
Tell me you have good news.
The universe never lets anything go to waste, or so said Lavoisier.
The law of conservation of mass.
In chemical reactions, mass is neither created nor destroyed.
Mass is neither created nor destroyed is the important part there, not the Star Trek reference, all right? But anyway, that's the idea. You're not making anything, you're not destroying anything. I'll talk about magic chemical ones sometimes, but that's just fake. There's always going to be some way to account for things going in and out. Questions? All right. Thanks for being here. See you at 1:10. Have a great day.